And then an obvious question is, what if these probabilities tend to zero slowly? Would this be non-zero in that case? This is a question where the second Borel-Cantelli lemma helps. So the counterpart of the first Borel-Cantelli lemma is called the second Borel-Cantelli lemma. What does that one say? It says assume we assume that E1, E2 are independent events. And such that now we assume that the sum of these probabilities is infinite. We emphasize independence. Here it is needed. Then the probability of En happening infinitely often is not 0. It's not 1/2. It's not 0.8. It is precisely 1. That's the second Borel-Cantelli lemma. To understand why and what's going on here, let's sketch a proof. Let's now study the complement of this event. So let's write E complement. And now we use the De Morgan's law, so which says that we can take now union M intersection N bigger than M, E and complement. Let's call this set here, let's call it Fm. So we have a union of these Fm's. My claim is actually that what I'm going to claim you now is that, sorry about this. The claim is that probability of Fm is 0 for all M. That's what I would like to claim you now. And well, if this claim is true, so then the union, then let's know if we can prove this claim. So then we know that the probability of E complement is by the union bound, it's less than the sum of M1 to infinity probability of Fm. If this is 0 for all M, so then we get 0 in the upper bound and we are done with the proof. So we only need to prove this green claim. So let's write it green here. We only need to prove this green claim. Then we are done with the proof of the second Borel-Cantelli lemma. How to prove this? So let's look at this. What's the probability of Fm? In a sense, it's the probability of the intersection N goes from M to infinity E and complement. Now we are looking at independent events. So these are independent. So in principle, we would like to write probability of E M complement times the probability of E M plus 1 complement times up to infinity. But these 3 dots doesn't work because we only define this independence factorization for finite intersections. So in principle, we would like to write this, but we are not allowed to do it. So let's clean it up. Let's not do what we are not allowed to do. how could we kind of approximate this infinite intersection by finite intersections? Well, using the usual thing, so let's write FML as intersection from M to some finite value L. And then we know that this FML, what happens when L grows and grows? When L grows to infinity, we are getting intersecting more and more and more. So these sets are getting smaller and smaller. So these are actually going down. And they are going down to the full infinite intersection in this way. And that's why, again, with the monotone continuity, we can conclude that probability of Fm is actually the limit when L goes to infinity of the probabilities of FML. That's the monotone continuity that we are using quite often when we go to say something about infinities. And now we can write this as each of these finite things factorize. Now we use the independence assumption here. And that's why we have the same limit, but now we have something which factorizes. So we have a product. N goes from M to L probability of En complement. To make this proofs a little bit neater, let's give this a name. So let's call, let me check. Yes, let's write this probability as 1 minus Pn. Let's call Pn as the probability of the En. And then what we can do, we can write this as it's the limit L to infinity. Then we have product 1 minus Pn here. What can we say about the product of 1 minus Pn's? I hope you had time to look at the quiz for today. So in the quiz, there was an approximation about 1 minus Pn. And well, how does the function look like? 1 minus P is a function of this sort. That's 1 minus P when P is there. How does the e to the minus P look? That's e to the minus P. So that's bigger. So we make an approximation upwards. We put here the product n from M to L e to the minus Pn. This is nice because that's the lim. Exponent function is good here. It helps with the products. So we get here e to the minus, then we have sum n from M to L Pn. Exponent function is also continuous, so then we can take the limit to the exponent. So it's minus limit L to infinity n from M to L Pn, and then we take the limit, so then that's the infinite there. So we have an infinite sum. E to the sum from n from M to infinite Pn. What do we know about this infinite sum? Let's recall what we assumed. We assumed that the sum from n from 1 to infinity of these probabilities is infinite. Yeah. We assumed that, so our assumption is that the sum from 1 to infinity of Pn is infinite. This was the assumption. So what about the sum from M to infinite? Is this finite or infinite? If the full sum is infinite, so if we cut finitely many values from the start away, it remains infinite. So this is infinite as well for every M. Yeah. So this one is here infinite, so I can write here e to the minus infinite. That is 0. Yeah. I'm using the extended arithmetic now. So in this way, we had an upper bound which is 0, and it was an upper bound for fm. So what's the conclusion? The probability of fm must be 0 if we have an upper bound which is 0. Yep. This was our green claim here. The green claim implies the full claim that this probability of E complement is 0. We are done with the proof. We are done with the proof, which is here, the second Borel-Cantelli lemma.